Good afternoon, everybody. Welcome to this webinar in which we are going to present the most relevant use cases that we've developed within the FLUIDOS project using the FLUIDOS technology. So the idea is in the FLUIDOS project is to create a transparent continuum where jobs and task processes can move around, can float in any place, either at the edge or in the cloud or even on the individual device in a completely transparent way. So FLUIDOS provide the technology and our partners, both within the project and through open calls, leverage this continuum in order to provide the value of the technology we developed. So this session has been devoted to present the use cases, not the FLUIDOS technology that we presented already. So the use cases, how they were developed and how they leverage this transparent continuum that FLUIDOS provides. So let's see our speakers. Sorry, wrong slide. So we start with Luciano Riccio, Open Calls, Datonix, Luca Macciani from Smarty, Open Calls, Dennis Lamotte, TerraView. TerraView is partner of FLUIDOS, Dimitri Brodimas, Patras, University of Patras, Open Calls, Christos Stefanatos, Open Calls, Lucas Granat, Robotnik is a use case partner of FLUIDOS, and also Luca Zuanazzi, RSE partner of FLUIDOS. I will give the floor to the first, Luciano, and please tell us what you've done.
Okay, let me share my screen. Okay. Oh, well, good afternoon, everybody. I am Luciano Riccio, and I work for Datonix, a leader company in southern Italy. And we decided to join this open call by proposing a use case. We call it Target, Intelligent Data Processing, the Continuum. And we joined as a consortium together with the Meditech. And my short agenda is this one. So I will present the two entities of the consortium and the reason why we decided to participate, to candidate us to participate to the open call. The way we performed the test of the FLUIDOS architecture and what we have found. So first of all, very briefly, Datonix is a little company focused on data management solutions. It is based in Napoli, in the southern Italy, and is a member of the ecosystem of Meditech. Furthermore, Datonix is the owner of a data management solutions for analytics called Query Object that we used in the past on both cloud and edge environments. On the other side, the Meditech is a competence center designed by Italian Ministry of Made in Italy with the objective to sustain digital transition policies for public administrations and small medium enterprises of the territory. We're talking about southern Italy and in particular Campania and Puglia regions that are also, let's say, partners of the consortium, together with the 7 universities of the territory and some private partners, big companies on the territory. Furthermore, Meditech has an ecosystem of 80 plus, more than 80 little enterprise on the territory, and Datonix is one of them. And Meditech used to work as an hub for the different actors in the territory, as an enable to put its assets as a service for the partners and also as a service provider. On the other side, Meditech is a member of three of the major EU association about data interoperability. I mean, FIWARE, International Data Space Association, and BDBA. Finally, and this take us to the reason why we participated, Meditech has developed a data platform for providing data services for both services provided by Meditech to others and for other partners. Why we did participate? The main feature we were interested in FLUIDOS in infrastructure was to empowering edge level application by enabling cloud resources to be used to perform some CPU demanding steps of the processes tasks, and more is to allow to keep the data on the edge, at least the sensitive data. So the idea is to let the edge level application use this data management solution, query object, and the fact that query object performs these IO demanding and CPU demanding processes was the key of the test we ran. Because these processes can overload the edge and could need the cloud resources to let it scale up, you know. So, so what is the way we ran this test? So we had an IP edge cluster with a single node in the example for the uh, for using the edge part of the system. So we had a local volume with the data, sensitive data in particular, and we used the FLUIDOS in order to offload uh, a pod in a cloud environment, and once the idea was to move some part of this data, the anonymized part of this data, which is called NRM file, to a shared volume. In this case, we use the Google Drive, but any sharing is okay. And let the offloaded pod work on this anonymized data. Once these processes have been performed, the result is moved back from cloud to the shared volume and finally used on the IP edge computer. So we had two ways moving of data, but we ensured that no sensitive data has been moved off the edge. And on the other side, we could have a scale up of the CPU capabilities thanks to the cloud node. So, what are the findings we have had First of all, let's say that Onyx has had the opportunity to test its product query object on a new kind of architecture. So has been able to provide this product to other kind of customers. While on the other side, the Meditech has had the possibility to expand the application fields of its data platform that is running query object by guaranteeing in using FLUIDOS the total compliance to GDPR rules, thanks to the anonymization of data to be transferred. Moreover, Meditech creates also a new kind of scale in its ecosystems that enabled Meditech to take part to other European projects. Among all, Cognets is a significant one. Um, Finally, for the future, the participants are evaluating the possibility to use the data platform as an intermediation platform for intermediation services. So I don't know if I was too fast because I was worried that 12 minutes would have been not enough.
You're perfect. So we have time for a question, actually two questions.
Okay,
So,
wonderful.
uh, you know,
Oh,
Fluidos is a research project. In a research project, there are usually nice idea and other things that could be improved. So, can you just briefly tell us what do you appreciated from Fluidos and what do you think it could be improved for the future research activities?
well, we have had at the first stage of the project some discussion with Francesco, our mentor from Politecnico di Torino, about the opportunity to empower the possibility to share disks other than share pods. I mean, by moving pods uh, containing part of data in order not to have the needing to share with Google in this case to access from the data from another system, another computing environment. But on the other side, this possible feature should be used with Granosalis because you can I'm gonna say you have always to find a trade-off between uh, the heaviness of a pod to be offloaded. As soon as you put on the pod too many data, you make it bigger, and so you have to find a trade-off, in my opinion, between these two kind of needings.
Perfect. Very clear. Thank you, Luciano.
You're really welcome, Fulvio.
Okay, so let's move to the second speaker. There has been a last-minute change. So the second speaker will be Giuseppe Zangari from Aruba Cube, and the project is DEAS.
Hello, everyone. I'll try to share my screen. Let me know if it's visible. Okay. Fulvio, can you see the presentation?
Yeah, it's PowerPoint, not the presentation, the slideshow. Perfect.
Okay. So I'm here on behalf of Luca Maggiani. We have participated to this open call together. I'm from Aruba Cube, and Luca was from Smarty, and our project name is Drone to Edge Analytics Services, and it's based on FLUIDOS. So I will go through a company presentation. I will explain you the scenario, an high-level architecture of the project, and then I will explain you some particularity that we have implemented and findings that we had. First of all, a couple of words about Smarty. I can say it's a great company, and they are focused on three pillars, which is connectivity. They are very strong on 5G private networks, but not only. They are very strong on the perception side. They have developed a lot of smart sensors, and they have also managed to develop artificial intelligence to combine these three pillars together and generate great value. Let's move to Aruba Cube, a company that I know a little bit more than Smarty. We are the cloud continuum company, in the sense that the entire company is based on the concept of creating the cloud continuum, because we believe that the cloud continuum will enable unparalleled agility, will be instrumental for a most efficient and smart use of resources, and also will accelerate innovation across all the industries. And our capabilities is for sure open source leadership, in the sense, especially regarding Lico, which is our beloved Kubernetes component. We are also the cloud native competence center for the Aruba SAP group. It's an Italian digitalization group, and we serve the group as the cloud native innovation center. The team is really strong on everything related to DevOps, and we use agile and collaborative framework for developing software and products. Okay, let's move to the DEAS scenario. Imagine to have a drone with a camera, pretty common nowadays. Imagine that the drone is taking picture, and imagine the drone with a little bit of computing capacity, and imagine that the drone has to do some inference on the image that is taking. Now imagine if, for example, this drone will be able to offload the inference of the images on the cloud. Could be fantastic, because basically you will achieve two main goals. The first one is that the entire computation will be really faster and more powerful, because basically the entire cloud power will be connected directly to the drone. The other goal that would achieve is that the battery would last a little longer, or the drone could be so the drone could fly for some more minutes and achieve its mission. This is basically the scenario of DEAS, and imagine that the drone is connected to an edge computing device via 5G. So in our case, the drone is connected with a 5G module through to the network that has also another edge computing module. So the whole idea is to basically use FLUIDOS to offload AI jobs from the drone to the cloud. This is the high-level architecture. You will see that on the left side, there is the FLUIDOS Node 1, which is the edge computing device. And it has the UI that we have developed for the project, and there's also an AI application. On the right, there is the FLUIDOS Node 2, which is the drone. And you will see that one of the component on the drone is what we call the DEAS orc, or the orchestrator, and I will explain you in a couple of minutes what is. And they are connected by this 5G cluster that is basically a 5G cell, and that basically generates a local 5G network where where basically the drone is connected, while the FLUIDOS Node 1 is connected to the 5G cell via a normal internet cable. The important, the particularity of this project is that everything that basically the cloud continuum enabled by FLUIDOS is developed on a 5G network that is, of course, dynamic. And that is why we have developed this orchestrator that is basically working on top of the meta orchestrator of FLUIDOS. And what is happening is basically that this component is scraping metrics from the quality of the network. The drone is basically checking continuously the quality of the network. And if the quality of the network is good, more than basically a threshold that we have seen practically that above a certain threshold, if the channel is good enough, basically the drone was offloading the AI jobs to the edge device. If the network is not good enough, the drone decided not to offload the job and run the job on board instead. And the quality of the network is assessed continuously, basically. This is the test environment that we have developed. On the left, what you are seeing is basically a 5G a component that is able to create a 5G cell and the computational device that is connected to it. On the other side, to simulate the drone, we have used the laptop connected to with a 5G model, basically. This is the dashboard that we have developed that show basically the topology of the network and gives real-time information on where the computation is running, if it's running on the drone or on the edge device. This screenshot is took during the demo, and this is the typical scenario with high signal quality. And as you can see on the graph, the 5G channel score is crossing the upper threshold, and this means that the quality of the signal is really good. And you can see that basically the node that is running the jobs is the LICO edge. It means that is basically the edge device connected directly to the 5G cell. It means that the drone is offloading the computation to the more powerful edge device. In this other particular scenario, you will see that the signal quality is really low, and this means that the drone decide to run the jobs on itself. And as you can see, the job is running on the Ubuntu machine that was simulating the behavior of the drone. And basically what we did was move around inside the laboratories and also the upper floor and the laptop, and letting the system run during this period of time. The result we have achieved is that basically we were able to do a real-time AI offloading using FLUIDOS and using this metric scraper, and it was working really well. We were able to demonstrate that the drone has some additional resilience in keep operating, keep doing inference on the images despite the quality of the network. We saw that the intelligent orchestrator that we have developed was good enough for the purpose of the demo. Was the ASORC was able to make the right decision based on the quality of the network itself, and it was basically a matter of tuning the threshold for not having too fast offloading in case the signal was varying too quickly. And also we have proved that the FLUIDOS framework can also be used in this particularly dynamic scenario. What can be improved of the FLUIDOS system overall? Would be fantastic if the meta orchestrator could also have this dynamic scheduling. Another thing that we saw that could be improved is the limited autonomy of the edge, in the sense that if you decide to offload a job to a node, the node cannot decide not to do it because maybe it has some different priority. It would be interesting to have the possibility to give the possibility to each node to decide if accept some jobs or not. And also will be fantastic to have better telemetry, of course, to orchestrate even more, even faster and better the overall offloading. And if you scan the QR code, you will reach the video of the demo where all this framework and all these steps are explained extensively. Thank you.
Thank you very much, Giuseppe. Any question from the audience? I don't have any question myself because you already answered what it was good and what can be improved. The good news in what can be improved is that at least 2 of the 3 items have already been taken by FLUIDOS and have already been implemented, but you were not aware because your project ended up earlier. So thanks for the feedback. We really appreciate it.
Nice. Thank you. Thank you, everyone.
Okay. So let's move to the third. The third use case is presented by Denis Lamotte from TerraView, who is TerraView is a partner of the FLUIDOS project. The floor is yours, Denis.
Yeah, thanks a lot. Let me share my screen first. So I'm from TerraView, with a company which is working in the field of smart agriculture, and especially I will talk about the use case where we were using FLUIDOS in our system, which is related to viticulture. So TerraView OS is a platform that we develop that helps growers in viticulture to make decisions based on analytics which are developed on the platform. And before the use of FLUIDOS, everything that we were running there was running on the cloud, and everything was deployed there. And it's a stack of the way it was working, like it's a stack of different like microservices which are responsible for the different subtasks that we have in our analytic pipeline. There are several challenges related to the use or to what we are doing in viticulture. First one being that usually the growers they have a low bandwidth connection, either because they are like far from actual antennas, or like because the infrastructure, like the network infrastructure there, when it's remote, they are not well developed. And this is a problem to ingest large data sets. So for example, when we do, which is a typical case that I will present in our use case, when we do drone flights, the quantity of data which is recorded and needs to be transmitted in order to compute different analytic is usually quite big if we want something, some analytic which is precise, accurate, and with a good resolution. So that's like typical problem that we have in viticulture. So one good thing there, one good idea there to solve some of those issues would be like to have the processing of the data being done as close as possible to the customer site. And this is this is just a summary of what I just mentioned again. So that everything like the software, everything was before on the cloud, and one idea would be like to have the software which is responsible for some of the steps of our analytic pipeline to be installed and operated on the edge, and some of the pipeline operated on the cloud. And we can do it by having some edge devices inside, directly inside the vineyard. So in the on site directly have some devices which are like strong enough to do some of the computations, and that way offload part of the data transmission, like remove part of the data transmission, because some of the work will be done directly on the edge device. And that's where basically TerraView can leverage the advantages of FLUIDOS, of like having this like offloading of part of the analytic pipeline done directly on the edge and edge device. So a typical scenario that I'm describing here in this slide. So usually growers they do drone flights every week. That's a typical frequency. Like having a higher frequency than this is most often not needed, because the information that they will get is not really impactful. But they have a limited bandwidth, so even for one drone flight, it can be a problem. And so the idea is to, as I said, like process the image directly on site. And once the images are processed and merged to produce like single image raster out of those of the drone flight images, then the data could be transmitted to the like more let's say like consuming like computationally intense steps where there is the introduction of some models that we develop, for example. So the already like the image can, instead of transmit all the image of the flight, we can transmit an already pre-processed image there that can then be analyzed and processed further in the cloud for the more evolved analytic, basically. And all of these results that we have, they are directly displayed on a platform that we develop, which we call TerraView-OS, the short name TVOS. And that's the solution that we have for growers. So here it's a bit of a summary of all of this. So the goal of the scenario was to place like high bandwidth and large data generating services directly on the edge, and especially like the image flight merging and pre-processing, which is representing a big quantity of data, and it doesn't require a lot of power, like CPU power, to do this. It can be offloaded on some edge device. But then the deployment and the visualization, all of this, it still happened on our cloud infrastructure, basically. So I went through then the demo that we built already for this, so which was using two part of FLUIDOS stack, so Kubernetes K3s for the management of the edge device, and then the cloud orchestrator for everything that we are running on the cloud. And a typical example of the use case was the following. So in terms of architecture at TerraView, we have something which is looking like this. So we have this like Google managed service on the cloud, which are managed by, which are like a Kubernetes 8 cluster. And where we have like infrastructure, like the tvOS infrastructure, which is about like 54 pods, and then we have what is on the customer, like the grower side, which is like one edge device, which is like handled by this Kubernetes 3 cluster. And then scenario will be that we want where the bandwidth is low, then the image processing will be executed. So we have this tvOS image processing step, which is happening before, was happening on the cloud, and now we can offload this part on the edge device. And the idea is that so the grower will upload the drone survey via some USB stick or like SD card, whatever it is, directly on the edge device. And then all the image processing, which is needed as a first step before computing any more evolved analytic, will happen directly on the edge device. And then this processed image will be then transferred to the main like centralized architecture that we have, where then it will be available for visualization on the like viewer platform that we have for the to show the analytics. So that's typical scenario that we were interested in, and that we implemented thanks to like FLUIDOS technology. And this enables, for example, so I put a small example that we were showing, that it enables basically to get some higher resolution image, because before, basically due to the limitation in terms of bandwidth, we were not able to transfer the data as it was recorded, but just like we needed to downsample the image. So doing this, we are basically able to have some higher resolution images directly visible on the viewer, just by offloading part of the job on the edge device. So yeah, so the good thing with this solution is that so it simplifies like a lot the deployment and the development of the different processes, and it makes TerraView independent from the actual running location actually. And also it simplifies a lot the interaction that we have between the different like components, like the different services that we have in the whole processing pipeline that we developed. And more than this, it also reduces like the resources that we need on the cloud. And so the total cost of the solution that we are building for is reduced, because the cost of cloud computation is reduced. So some of the results that we didn't have the KPIs for all of this, because it's still part of the project of this year. But what we can say that will be the results of all of this scenario is that the data transfer is really reduced, like by one order of magnitude, while the processing time being like the same. And since we do less processing on the cloud, we have also a reduction of the cost of the processing on our side. And all of this is done through like in a way that if we have disconnection from the cloud, it does not impact the operation there. Like then the transmission is just done when the connection is reestablished. But we don't have we are not subject to disconnection from cloud compared to what we were able to do like before using the FLUIDOS technology. And that's it for my presentation. So it's like I did a short summary of what we were doing over the last years. And yeah, if you have some questions now, I can answer them.
Perfect. Thank you very much, Dennis. Any question? Okay, no questions. I don't have question myself. We are a little bit late, so we need to move to the next speaker, who is Dimitris Brodimas, University of Patras, from one of the open calls within the FLUIDOS project. Dimitris, the floor is yours.
Hello, everyone. Okay, just let me share my screen. Okay, I believe that you can see the screen. So my name is Dimitris Brodimas, and I'm from University of Patras. I'm my PhD candidate there. University of Patras is located, as indicated by its name, in Patras in Greece. It is the third biggest city in Greece, and as you can see, we are one of the biggest campus in the country. I come from the electrical and computer engineering department, and specifically from the applied electronics laboratory. So our main research domains are edge analytics in terms of AI, machine learning, and nowadays with generative AI and agentic AI, with a lot of activity in distributed learning over embedded hardware mainly, heterogeneous ones, passing through different architectures with resource-constrained devices that we need real-time response and high data rates. In those devices, we are mainly targeting TPUs, GPUs, and FPGAs. We reconfigure them, and we try to advertise them in higher level of architectures throughout the whole continuum. So in the edge cloud orchestration, we mainly operate in the cloud native environment through inter-cluster management, continuous monitoring, and optimal workload placement. Having said that, I pass to the use case where our goal is to automatically inspect the power lines and towers in the distribution grids using AI-enabled drones in order to enable fast, accurate, and cost-effective predictive maintenance. The domain is the renewable energy infrastructure and specifically the distribution grids. We target to do the predictive maintenance, enabling the condition-based assessment, increase asset life, and minimize the outages in the distribution grid. The methodology that we used in order to implement this goal is through hierarchical learning, where we used lightweight AI models on the drones in order to enable the real-time analysis and full deep learning models running along them in the edge cloud servers for more complex cases. So we are targeting the cloud edge synergy in order to dynamically select the edge nodes based on the drone position in order to reduce the latency, bandwidth costs, along with any outages in the network. The main challenges that we tackled was the limited drone capacity in terms of compute and memory, the dynamic drone paths that affect the optimal server selection in order to support the drones, the real-time latency constraints, and the operational cost efficiency of the overall solution. The validation took place in the University of Patras with the real flight data and simulated network and server conditions. So, some words about the hierarchical inference. First of all, we have the common centralized learning where we have all of the data from both the drones and the workers in the domain passing to the cloud servers. We have the edge learning where all of the data do not go to the main cloud server, but they are distributed to the worker in the field. And we have the hierarchical learning where we have both solutions combined in one, with some of the data traveling to the edge cloud and some of the data remaining to the edge. So here you can see a little bit of the pros and cons of this hierarchical inference. Mainly on the cloud, we have better accuracy and more processing. In the edge, we have more privacy because the data do not leave the devices. We have better reliability and somehow good accuracy. And the hierarchical AI, we have the most improved, let's say, qualitative metrics as we maintain the privacy. We have less latency, increased reliability, less communication overhead, and less application cost. So here is a view of our application. You can see that we do have a lot of microservices running over the edge servers and on top of the drone. We get the video at first, then we do the extraction, we sample it, we detect if something is wrong on top of the towers of the distribution grid. We do a classification on top of them in order to be able to say if those towers are healthy or not. And then we inform the maintenance crew. Essentially, what differentiates this use case from a pure edge use case is that when we do not have um, the needed results and when the accuracy drops, we have an offloading decision that gets those algorithms from running on top of the drone at the edge servers, okay? And then we do the same things in order to increase the accuracy of the algorithm, but maintaining the decreased cost of running everything at the far edge. Just some additional things are that essentially on the drone we have a Raspberry Pi that does this computing along with a Halo accelerator, while at the edge server we have the commercial off-the-shelf servers supporting the drone. Okay, now passing to the FLUIDOS integration. Here is a common path of the drone that flies in different follows different paths in order to reach the destination and following essentially the power lines of the distribution grid. Those power lines are covered by different, let's say, networks like 5G, having G-Node Bs with integrated mobile edge computing supporting those G-Node Bs. So we assume that behind every G-Node B, the mobile edge computing is ready to host our application and be able to support it when we do not have the needed accuracy on the drone, on the algorithm running on the drone, on the Raspberry on the drone, and we need to drop these applications to the edge servers. So we have here a stripped architecture, okay, with three main microservices: the camera application, the decision app that we talked earlier, running over the consumer, over the Raspberry Pi, and then when the decision so what we did was to have a dynamic app migration using the FLUIDOS software, and we contributed to it. Essentially, when we have a common point, when we have a new network, and meaning that we have a new provider, and we discover it, we subscribe the cluster, and we say that, okay, we are ready to migrate our applications on this provider. Now, when we go outside of of the range, the initial range that we had, we migrate the app. Okay, so we do something like that. We take the decision and we say that, okay, we move on to the next provider. Okay. And regarding the results, we successfully integrated the FLUIDOS node over some Raspberry Pis with ARM64 architecture using K3s clusters. We exploited and developed an automated way in order to detect clusters and subscribe them and perform some migrations when suitable. Finally, FLUIDOS enabled the support from the closest mobile edge computing following the path of the drone, minimizing the network latency and increasing the availability of the centralized components. I also have the video here. which, okay, it doesn't work, but no worries. It is on the YouTube. You can find it there and have an overall look at our use case. Okay, so that's all from my side. Any questions? Also my email if you want to send something later.
Thank you, Dimitrios, for your very clear presentation. Just brief, also in your case, the question about what do you feel it's a good idea in FLUIDOS and what do you feel it should be improved in FLUIDOS?
Yeah, to be honest, what we also described in our initial idea about this use case is to take the decisions also based on the latency, the router latency of the in terms of the providers and the consumers. Okay, so this artifact was not ready at the time of the experimentation and the demonstration. So I believe that, yeah, this would be the most useful thing to have in our use case.
Thank you very much. So it's time to move to the next. The next speaker is Christos Stephanatos from Parity Platform. It's another project funded under the FLUIDOS open cause. Christos, floor is yours.
Thank you, Fulvio. Hi, everybody. I'm Chris from Parity Platform. I'm starting off with a company intro and our research interests. So first of all, on the commercial side, our company has developed in-house and commercialized EV loader software. This is a software that is active in Greece and the United States that is used to monitor electric vehicle charging stations, monitor and process payments. So this is the main thing we start with, and the needs of our main commercial products feed into our research interests and define our research interests. Just some credentials of our main clients. We mostly work with the hospitality sector and retail shop sector, like grocery chains that install electric vehicle charging stations and want to attract users to those locations. And therefore, our research interests that come out of our main commercial activity is one, cybersecurity applications in the EV charging domain. EV charging is growing rapidly, and more sensitive infrastructure and sensitive services like law enforcement, hospitals are being dependent on electric vehicles. So this creates a huge gap in terms of cybersecurity. And the first phase of electric mobility was having applications that work and can monitor charging stations. The next phase, in our opinion, will be securing this infrastructure, because currently it's very vulnerable to cyber attacks. And we are participating in some open calls and Horizon programs on this side. Another research interest on our side is guidance for electrical installers, because we monitor and sometimes are involved in the installation of charging stations. We need solutions that can provide guidance and also allow us to verify whether an installation has been completed correctly. So we have an application that runs on Unity. It can be run on headsets or AR compatible mobile phones, and allow the electricians to receive real-time information related to the installation of the charging station or other electrical device that they are installing. And finally, some larger Horizon Europe projects we are participating in as partners. There we act as dataset providers, providing anonymized datasets from more than 5 years of charging sessions, because we have been active as charge point operators for more than 5 years. and we develop algorithms to ensure that charging takes place at time intervals that make sense for the electrical grid. For example, when there is surplus from renewable energy, it makes sense to have some kind of incentive for charging, like reducing cost and so on. And in the context of those programs, we have worked with large universities and stakeholders in the energy industry. And now moving on to FLUIDOS and our research interest here, what created the idea for our proposal. Looking into the EV charging infrastructure, we have identified two main challenges. The first one is that if we want reliable EV charging infrastructure, we will soon have more sensors from different vendors operating on the same charging stations. Right now, the only information the charge point operators can have is whether a vehicle is connected to a charging station, whether it's charging. So anything related to the flow of electricity and cable being connected to the charging station. But for example, if there is a car parked in front of the charging station, the charge point operators do not have this context information within their system, which is a huge drawback. And in order to have this kind of context, you need additional sensors like proximity sensors, cameras, and so on. But the bad thing about those sensors is that it's a different interface than the one you use to monitor your charging stations. So the one thing you need is a solution that unifies different, to say it better, different kind of sensors and be in a position to visualize all those sensors and all those data in an understandable dashboard for the operators and facility managers of those locations. And the second challenge is the reduced availability and reduced quality of service we observe many times, because currently all those locations rely on Wi-Fi or generally cloud connectivity to a cloud server. So at time intervals where there is connection loss, it's highly likely that we will have data loss and significantly compromised operation. Some charging stations have some kind of fallbacks to operate offline, but most of them have no kind of fallback. So loss of cloud connectivity means lack of availability to the service. So again, we needed a solution to ensure that somehow, even if we lose cloud connectivity, we can ensure continuity of data and continuity of service. Just some items here. You can see that it's not only the charging station. You can have smart meters that monitor the total energy capacity in the building. This kind of information, you need to somehow monitor it in a unified dashboard. I will talk over I won't play the voiceover in the video. I will just talk over the video to explain what we deployed here. Here in our office, we deployed Raspberry Pi devices connected to temperature sensors. We wanted to simulate the action alerts that should be triggered if a charging station has higher temperature than expected. So what we did is that we have those edge devices that monitor the temperature of the charging station, and this information is processed at the edge, but also relayed in the cloud. And in both cases, even if cloud connectivity is lost, action can be taken. So if temperature rises and cloud connectivity is lost, the charging station will still receive a decreased charging capacity command. And here are some of the dashboards that were deployed. The most important outcome was a custom Grafana dashboard that aggregates information from different IoT devices and enables the facility managers to monitor this kind of information. And also, this context information enables the facility managers to make some decisions are made for them, but it also enables them to make better informed decisions, like For example, if you can see from the proximity sensor that you have a car parked in the charging station, but no charging activity is happening, this is a clear signal that somebody has taken over the charging station, to make a super simplified idea of what context information can provide. This is a graph of the deployment using FLUIDOS components. You can see on the upper side, you can see the continuum between our cloud, edge devices, and the charging stations. And here is a screenshot of the dashboard that aggregates information from charging stations and other sensors, including temperature, for example, as shown above. The FLUIDOS components we utilized was Discovery Manager to monitor the Raspberry Pi devices we have deployed across different locations, Node Orchestrator to ensure that the services that are intended to run at the edge are running at the edge, and vice versa. And if there is a service outage from the cloud, that the edge service continue running, and telemetry service that feeds information from different sensors to the custom Grafana monitoring dashboard. Just some benefits we found with FLUIDOS. It's a quick setup using open source and widely accepted tools. It allows rapid setup, and the end objective was achieved. We achieved better service quality and data availability even when cloud connectivity was lost. And I'm also sharing the GitHub here, and I believe the code we have shared in the GitHub is very easily adaptable to other verticals, especially if you want to monitor data from temperature sensors connected to Raspberry Pis. You can almost take our code and use it with minimal changes on your situation. And some ideas for further research. My colleague Alexis Karadimos, who is our CTO, collected the data from the experiments we performed with the Raspberry Pis and produced a paper that is going to be presented this July in Croatia. So this is a very promising research area for us, and I believe it's yet underexplored. I do not believe we have reached the full capacity of information and sensors we can utilize in the EV charging infrastructure, in my opinion. This is my email and all my contact details. Happy to discuss anything related to the project or future projects with you. Thank you so much.
Thank you very much, Christos. I have a question. Actually, you use a lot of FLUIDOS component, and you highlighted already the advantage of the FLUIDOS platform. But what about any missing point or something that can be improved in the future?
On our side, I'm just transferring the feedback from Alex, who is the CTO and had the most contribution in this. I think the session we're having today, where we see FLUIDOS project in practice in different domains, is very interesting. If you could add even more practical use cases explaining usages of these components in other domains, I think we could attract even more developers. Because when you look at a higher level without diving very deep into the documentation, it might not be clear to the average developer. Okay, I want some ideas. How can I apply these tools in my use case? So some use cases would very specific use cases would help.
Thank you very much. Okay, so let's move to the next speaker. The next speaker is Lucas Granat from Robotnik. Robotnik is one of the partners of the FLUIDOS project. working with FLUIDOS since the beginning. So Lucas, the floor is yours.
Let me share my screen. Hello, everyone. Here. You should see my screen. Yes. Hello, everyone. I'm Łukasz from Robotic Automation. We are part of the FLUIDOS project. We are having the logistic use case to present the capabilities of the FLUIDOS system. Who are we? Who is Robotnik? Robotnik is the mobile robots manufacturer and also a little bit of integrator. We have the vast gamut of mobile robots from that are applied in the fields from logistics to from inspection as well to mobile manipulation. In this project, we are focusing mainly on the Arbiteron. This is the left, second from the left robot. And also we used for the test and the RB Watcher. These two in the middle. What is the environment that we have for our use case? We are using the Arbiteron robots. We are using two of them to have the example of the fleet. The software the control of the robots is based on the ROS2 Humble, which, as the ROS is based on microservices, allows us to decorise different components of the control principles like navigation, localization, handling of the hardware, and so on. The tests are performed in the Robotnik warehouse, and in the local infrastructure, we have a few servers where we can also apply the edge clusters. So we have at least 3 clusters in here in working. In our use case, we have 2 RB Teron robots who are transporting the load from one place to the other. And they perform the normal operation when they can be in operation waiting for the new task or be in charging. And what we want to achieve is to optimize the CPU and battery usage of the mobile robots, because this is actually a very important thing for mobile robots. And we want to integrate with the FLUIDOS platform and use the intent-based orchestrator for managing the resources on the robot. We are still in the process of integration of this use case. However, we performed previously some tests based on the RB Watcher, called also previously Summit XL. And basically, how we use the FLUIDOS platform in our use case, we want the FLUIDOS platform to turn off unnecessary elements of the software when they are not used. For example, if we have the robot charging, then the navigation, localization, and feedback from the sensors is not necessarily useful at that moment. So we can power it off to make sure that the robot is charging faster, save the CPU load and battery those always also. And in moment when we have pending task and for example, we exceed the 50% of the CPU load of the robot, then we want to share the load from the robot, for example, share some navigation computations to the edge cluster or to the other robot in the fleet. And from what we already have seen in our use of the FLUIDOS platform with our robots, we have a few benefits, and that quite obvious, as we have the cluster based deployment. It really reduces the time for deploying the whole fleet, as usually in that case you need to have more setup involved for each robot, where in here we can just quickly change few parameters and it's working the same for all the robots. This also have impact on the easier maintenance as different models of the robot are Dockerized, and then it's way easier to make the version control that is still compatible with the fleet management system. As we are turning off the elements that we are not using at that moment or offloading them to other devices, we are reducing the CPU usage and battery usage, which extends the autonomy of the robot that allows the robots to work longer without the need for charging. That is great because the time when the robot is charging is usually kind of waste time for the robot because it's not able to perform any task at that time. When we have possibility to reduce the CPU usage and the battery, it also opens the door to reduce the costs of the hardware, to give the hardware that provides the less computational power, but also it opens the other way of the development, where we can give more flexibility to the robot's hardware. For example, instead of using just 2D localization, we can apply the 3D LiDAR-based sensors, where the computation required for this kind of mapping and localization is way higher. Spreading this computation along the clusters from the other robots or from the edge really benefits this solution. The same of implementation of different AI models, for example, for obstacle detection or human detection for the safety reasons, or that has impact on the path planning. This is also like a great thing that we can do in here. And as we were doing the preliminary tests on the RB Watcher, and now we are transferring everything to RB Terons, the architecture of the control is in principle very similar, and that really allows for scalability of connecting the same solution for different kinds of the robot that perform different tasks. In here, we are taking care of logistics use case, but the same setup could be used also for the robots that perform the inspection tasks or for mobile manipulators, wherein they're actually probably would be also useful in situations when you need to perform the more heavy in computation tasks like object detection before picking and similar. Well, thank you for attention for presenting our use case, and I'm happy to answer any questions.
Thank you very much, Lucas. Given that you are part of the FLUIDOS, do you see any advantage in terms of service that you can provide to your customer thanks to the FLUIDOS technology?
For sure. Basically, and the industrial robots, considering the mobile robots that are used in the power plants, they usually need to work in the closed network. And this actually is very beneficial for FLUIDOS platform because it provides the proper safeties for the information transfer and allows us to offload fairly easily the computation power to the edge devices without the need to use the cloud, because not all of the clients would like to have their data passed through the internet outside of the network of the power plant fabric and so on.
Thank you very much, Lucas. We can move to the last speaker. So let's share the screen. The last speaker is Luca Zuanazzi from RSC. It's a partner of FLUIDOS working on the energetic sector. So let's give the floor to Luca and see how they would like to use FLUIDOS in their use case.
Thank you, Fulvio. I will just share my screen. Okay. Perfect. Okay, so good afternoon, everyone. I am Luca Zonazzi, and welcome all to this webinar, and thank you for your participation. As Fulvio was saying, I work for RIC, which is an Italian research company focused on the energy sector. At RIC, we do many things, from assisting the utilities of the energy sector to supporting the Italian regulatory bodies. And inside FLUIDOS, we are responsible for the intelligent power grid use case, which is one of the 3 main use cases. You can find it on the FLUIDOS website. And more specifically, we are investigating the potential advantages of the adoption of FLUIDOS inside the energy sector. So I start with a bit of context. So due to the energy transition, power grids in the last decades have evolved from a traditionally centralized architecture to a modern and decentralized one. As you, I guess you all know, in the past, we had a small number of big and controllable power plants generating power for all the final users. And now instead, power grids are more and more permeated by renewable energy sources, which are great for the energy transition, but not so great for the grid stability, because they are unpredictable and decentralized. For this reason, it's more and more important to monitor distribution grids. And this requires an innovative ICT architecture to handle all the measuring devices and the measured data. So containerization and orchestration techniques are very popular nowadays, and they offer great advantages in terms of automated deployment and resilient management. And they're also being applied in this context of the digitalization of the energy sector. So now we are ready to understand the intelligent power grid use case. So a promising monitoring infrastructure is the following here, which employs phasor measurement units, also called PMUs, which are sensors that are physically attached to the power grid and displaced in critical points of the power grid. And they measure several quantities from the frequency to voltage, current, and phase, and so on. For simplicity, we can just call these measurements phasors. These data are then sent to the phasor data concentrators, or PDCs for short, which are services that aggregate and pre-process the measurement data. Notice that these are just services, so they can run on any computational device. And in general, these services are configured according to a hierarchical architecture, as shown in this picture here. So we have local lower level PDCs running closer to the field, and then a higher level regional PDC running in a control center. In the end, all the measured data are used by a variety of applications. Here, I just wrote the grid state estimation, which is one of the applications that simply uses the data to compute an estimate of the status of the grid, and then this status is used by other applications. And this infrastructure has already been deployed in the transmission grid in the past, but now now we are trying to transpose this idea to the distribution grid, which is where the renewable energy sources are being deployed. But this transposition is not simple, it's not trivial at all, because the distribution grid is much more complex and wider, so it's more difficult to monitor. So for example, here I wrote that the number of PMUs, the number of sensors grows from the order of hundreds to the order of thousands. So this is one of the first challenges we encounter. But this is not the only one. There are a lot of other challenges that we must tackle in order to transpose this architecture from the transmission to the distribution grid. And this is the main problem that we are trying to tackle with FLUIDOS. So we can summarize these challenges in these 4 points. First of all, we have resilience. As we all know, the power grid is a critical infrastructure, and as such, it must be very reliable. So, for instance, managing faults or planned maintenance should be automated. Obviously, we don't want for an ICT outage to escalate into a power outage. Okay, so resiliency is very crucial. The scalability, we already saw this in the previous slide. The number of PMUs is very high, of the order of thousands. But by scalability, we do not only mean the number of devices, the number of PDCs that must be run, but also the management of the infrastructure. So, for example, we may have a security patch to deploy, or maintenance, or an upgrade. And all of that, if we have a very big and complex architecture, is complex to do. So this also pertains to the scalability point, the scalability challenge. Then we have latency. So mainly the application that I was talking about are real-time applications, and this means that we have really strict latency requirements. By latency here, we mean the time that occurs from the time that the PMU measures the data, and it has a GPS module, so it attaches a very precise timestamp to the data that has been measured, and all of this processing chain occurs. So the data are sent to the PDC, are processed, and then to another PDC, and so on and so forth. And all of this counts to the final latency experienced by the final application. And this must be of the order of tens to maximum hundreds of milliseconds. So we have a very strict constraint here. And then also we have, for example, cybersecurity. We know the power grids, as I said, is a critical infrastructure, so it must be protected from any type of attack, and not only physical attack, but also cyber attack. So cybersecurity is very important. Luckily for us, FLUIDOS help us to tackle all of these challenges with its specific features. So, for example, the computing continuum is one of the core functionality of FLUIDOS, and thanks to the computing continuum, we can improve the resiliency of the monitoring infrastructure. We can obtain this because, for example, if we have a fault or a maintenance, we can just move or reschedule the PDC application to another node. We can just acquire some new resources and move the application seamlessly without interrupting the phase of data stream. And this obviously helps to increase the resiliency because we keep a constant monitoring to the grid. Then another key component of FLUIDOS is the intent-based orchestration. This orchestrator can be configured to obey two very specific and custom intents. And for example, as intent, we can say that we want to minimize the latency experienced by the end application. And in this way, the PDC will be deployed in the optimal point so that the overall latency is minimized. This helps us to tackle the second challenge that we had. Also scalability is tackled by the multi-cluster architecture of FLUIDOS because thanks to this architecture, we have a very high number of nodes that we can connect, and also the maintenance and all the scenarios that we talked about before can automated by the FLUIDOS computing team. All the other features of FLUIDOS can also be used to enhance the resource optimization, for example, or the cybersecurity that we talked before. So all of the challenges are tackled by the FLUIDOS computing continuum. Now I just want to focus a little bit on the resiliency aspect and show you a brief demonstration that we have prepared to show that the resiliency is actually improved. And to do so, we prepared an experimental setup, which is this one here. We used our experimental test facility that we have, which is an experimental microgrid that is monitored by 5 real facial measurement units. And the data is then sent to 3 different servers that are located in our laboratory here in RSC headquarters. And we use these 3 servers to build a computing continuum, FLUIDOS computing continuum. And more specifically, we have 1 consumer and 2 providers. The consumer, as the name says, consume the resources offered by the 2 providers. And so a higher level PDC is run on the consumer, and 2 lower level PDC are offloaded by the consumer onto the 2 providers. And also a replicated database is instantiated. This is needed for the PDC to run. In this picture here, I just show 1 lower level PDC because the other one would act just as a spectator. So this is the overall infrastructure that really matters. And if we have, for example, an operator, an electrical operator that wants to interact with the power grid, it can do it with the graphical user interface of the PDC, connecting to the backend, which runs on the specific node that he wants to connect to. So the first scenario that we tried was to simply simulate the maintenance or the failure of one of the lower nodes. In such case, if we have a fault, the PDC that is running on that node is automatically rescheduled by FLUIDOS onto the other one. And this happens automatically thanks to the FLUIDOS control plane running on the consumer node. And this helps us to, as I said, increase the resilience because the monitoring the data stream is not interrupted. Or, well, we measure the interruption time. Here we have a Grafana dashboard where we have monitored the data stream. And since this happens automatically, there is no need for the operator intervention. The recovery time is very, very fast. Here we measure something of the order of less than a minute. Let's say less than a minute. But then we have another scenario that, in my opinion, is very much more interesting, which combines multiple subsequent failures. So let's imagine, as before, that we have the same architecture, and let's say that the provider running the PDC is isolated from the rest of the computing continuum. We can simulate this isolation, for example, with a connection interruption or simply with an unavailability of the consumer node. So let's say that the consumer node is unavailable and the provider is isolated. And then we have another failure. Let's say that the lower level PDC crashes for some reason. Then even if the provider is isolated, it is able to restore the lower level PDC automatically. And this is an increased level of resilience that cannot be achieved with just, for example, Kubernetes technology alone. The FLUIDOS computing continuum is needed because only in this way, all the nodes always maintain their decision-making capabilities, even if they are isolated from the rest of the computing continuum. And here we have some visualization of this scenario. We simply deleted the pod of the isolated node and it automatically restarts. And we have also a Grafana dashboard showing that the downtime is of the order of 20 seconds or so on. So to conclude, we demonstrated the improved resilience of the ICT infrastructure, but also FLUIDOS, as I said before, help us to tackle all of the other challenges that are present in our use case. And that is it for my presentation. So if you have any question or otherwise, thank you for your attention.
Thank you very much, Luca. No questions? Okay, I have actually one question, pretty difficult if you can answer. Your results are definitely interesting, at least to me. But the energy sector is, let's say, slow to evolve. So it's very conservative. Do you think those kind of cutting edge technologies have a chance to be deployed, or maybe not? We have to think about something more, let's say, consolidated.
Well, obviously, I don't know the answer because nobody knows, but if I try to imagine what can happen, I would say that this is a very slow process. So it will happen by steps. So already the virtualization techniques like Docker and Kubernetes are not yet used in the energy sector. So that could be a first step. The interest is rising, of course. They are seeing that there are a lot of advantages in using these virtualization techniques. So in my opinion, it will just take time, maybe a lot of time, but in the end, the virtualization techniques will be used, and maybe also something more advanced like the FLUIDOS computing continuum will be used, because in the end, the advantages are there. So it's just a matter of time of recognizing it and deploying it on such critical infrastructure.
Thank you for your answer.
You're welcome.
So it seems to me that we arrived at the end of our meeting today. Thank you for all of you who participated first in the project or in the open call. So dedicating quite a lot of time to this idea and sharing also your results within the FLUIDOS community, and today also outside the FLUIDOS community, given that this webinar is public, so it will be available soon on YouTube for the general audience. Thank you very much, everybody, and we can close the webinar here.